Class number 3 is going to be mostly about SIMD, but we'll also be talking about assembly. First up, assembly. Used to be we'd have to write everything in assembly. It looked something like this. Lucky for us, nowadays we don't have to deal with that anymore. We have C++, that most everything is going to be written in, but I still expect you to be able to read the assembly. Maybe you don't have to write it so much, but yes, you do have to read it. And why is that? When you're debugging, you'll have to analyze the situation. You'll have to read a crash and look at the code and explain, why did this crash? Why is this doing what it's doing? Also, I'll expect you to be able to look at the disassembly and answer the question, is the compiler writing efficient code here? I started with some C++, like here's some C++ and some C++. And what did the compiler turn that into? Did it do something that I didn't expect? Maybe it did something that I think is really stupid, and I should really go back and look at this code to see why it ended up so complex. Could I have written that in a different way to give the compiler a clue of how to write that? So when you get in this situation where you're the one on the team that has the crash and you're in release build or something, maybe you don't have the symbols, maybe you're forced to look at the disassembly and answer the question, what is this code even doing? If you never learned how to read any assembly at all, then you're going to be a sad puppy. All right, so quick overview. Registers. Let's start with registers. Everything, of course, in a computer is some kind of memory. Every number is stored somewhere in the computer. The registers are a special kind of memory. They're memory that's bolted directly onto the CPU, and it's not just like a bank of multi-purpose memory. The registers are where the math happens. When you say, computer, I want to add these two numbers, there are registers that it will pull the numbers from, and it will stick the answer in a register. It cannot work directly out of memory for all of these things. Most things need to be in one of these registers. Okay, so we have for the x86, and that means the Intel chips. It means like, PC. This is actually the 32-bit architecture that I'm going to go through here. It's been extended, of course, now to 64 bits, but it's the same deal. Okay, so these are the general purpose registers. Really, you're going to see the EAX, the EBX, the ECX, and the EDX. What does that mean? Okay, X, just, let's go this way. It's A, B, C, D, right? This is the core of the difference between those. Where does that come from? Back when we had an 8-bit machine, we'd have the A and the B register, and maybe the C and the D register. And when you go to 16 bits, then we had two 8-bit registers for each of those letters. We had the A high and the A low. So this is the high 8 bits and the low 8 bits. And then, of course, we went to 32 bits. And, well, in 16 bits, we had the AX register, which is all 16. But now we're in 32. We don't even talk about those, really. Now we're going to see everything's going to be in 32 bits. So we'll use the EAX, which is the extended AX register. It just means 32 bits. Okay, so we have these four just general purpose. We're going to use them for math and stuff. You'll see a few patterns of what gets used for what, but for the most part, you want to add, subtract, you want to multiply, you're going to be using these things. You want to use a pointer. Yeah, these will be pointers too. They'll go in here. All right, some other things to point out. This one is going to be interesting. The ESP, we're going to be seeing that one from time to time. That's the stack pointer. So that's where on the stack, where's the stack currently, right? Where's the stack? When you push something out of the stack, you'll have to move the stack pointer up, right? Okay, so those are registers. Here are the basic x86 commands, and we'll be talking about the assembly language forms, not the machine codes, not the binary, right? Not the numbers. These are we'll call them mnemonics, or just short little words that will turn each command into one of these words. So basic form, move means to move a number from memory into a register, or we'll also use the same word to move from a register out to memory, or you can even move from one register to another register. So just move a number around. Okay, add, okay, that's pretty obvious. We're gonna add some numbers, and there's a subtract, there's a multiply, mul, M-U-L, mul, div, D-I-V. Okay, these are a little bit harder. This is compare two values. This is test. What that does is it does a bitwise AND. You don't need to memorize this. Test, when you see a test, that looks like part of an if statement. Right? Compares and tests, those are logic questions. They set flags. They don't actually, the test instruction doesn't actually write a result anywhere, but it sets flags inside the chip that a following jump instruction can react to. So J, all the ones that start with J are jumps, like jump not equal is JNE, or jump if equal is JEQ, jump greater than, jump GT, things like that. There's also a jump, JMP, which is just an unconditional, just always jump. So you see something that starts with a J, that's going to be a jump. And what a jump is, that's a go-to. That just means, so for example, let's look at JNE. If the previous compare, test, whatever, did not end up with a 0 result, then we will take the jump. We'll do that jump. Although if it did end up with 0, then we will not take the jump. So that's what that means. Okay, other useful stuff, call. That's pretty obvious. Call a function. You see a call, that's calling a function. And then there's push and pop. Those are for the stack. So we can push and pop stuff on and off to the actual stack, the machine's own stack. You will not always use these instructions because we do have that ESP register that you can just manipulate directly. Okay, let's look at an example. Okay, what are we seeing here? What we've got here is a very short C program or C++ program that I have compiled in Visual Studio, and then I have used the disassembler to show the assembly code that was created when I compiled the code. And the Visual Studio disassembler was kind enough to interleave the original source code with the code that it created. So this line turned into these 3 lines. This line turned into these 3 lines, etc. Right? Okay, so let's take a quick look at the anatomy of the disassembly. First thing here, this is the address of the instruction. These instructions are actually just numbers sitting in memory, just like anything else. This is the address in memory of where this instruction begins. And then the next instruction is here, next instruction, next instruction, next instruction. You will notice that they are different sizes, which is kind of goofy. Each instruction has different numbers of arguments, and they may take more bytes than another instruction to store. And so the disassembler is going to work all that out for us. So it's rather complicated if we wanted to try and do it ourselves. So this is really going to help. This disassembler, the Visual Studio disassembler, shows us the address, then the function, the mnemonic, it's the function that we're going to execute, and then the arguments. And the argument order for Visual Studio is destination, comma, source. So if anything, in any operation that has a destination, it will be the first argument. Okay, So let's look at this very first instruction and try to understand what that says. It's a move of some kind. I mentioned the move instructions, and let's just not worry about the ZX, right? Just don't pay too much attention to those. It's just going to be too confusing to try and memorize everything. But a move instruction, we know what that does. That's going to move into the EAX register from some pointer. What pointer? There's an address. The H. What's the H stand for? That stands for hex. So the disassembler, instead of doing 0x number, it's going to do number H. But that means hex. Okay, so we go and we get some number, and it's a byte, and we stick it into the EAX register. Okay. Next up, we're going to do a test on the EAX register. It's going to be compared with itself. Why are we doing that? Why are we comparing a register with itself? Of course, the register is equal to itself. Well, what it's really doing is testing to see if that value was 0. If the value was 0, that would equate to a false, right? If the value is 0, then that means whatever is in EAX is interpreted as a Boolean, means false. Let me stress that real quick. In C++, the rule for a bool is that if it is 0, it is false. Anything other than 0 is considered true. Okay, so we test the bool against itself, and that will set the 0 flag if it was 0. If it was false, then that will be marked as equal to 0. So the next instruction says jump if equal. So JE, I probably said it was JEQ in the previous slide, but it's JE. So jump if equal. So if this test was equal to 0, then we're going to jump to, where are we going to jump to? We're going to jump to, this is the name of the place we're going to, which is somewhere in the game update function, 70 hex bytes in, and then there's the full address written there for us. Okay, what does this line mean? This says, if the previous test we did had a 0, it returned a 0, then go here. Where is it going? Let's find that address. Here it is, 495310 hex. That's here. So if it was false, if BAD is false, go here. If it was not false, we go here. So in other words, if BAD is true, go here. All right, so let's read this instruction. What is this? This is a move, straight up regular move, moving into the EAX register from a pointer. It's a D word pointer. That just means it's a 32-bit. So it's moving from a pointer called A. It has a name for this one, so that's good. I don't know. I honestly don't know why it didn't give me a name for that one. Couldn't figure it out, apparently. But it figured this one out. A is loaded out of memory into the EAX register. Great. Next line. We're going to add into the EAX register from, going out to memory again, to memory B. So what did we just do? We loaded A in to EAX. Then we load B in and add it to whatever was already in EAX. So EAX now holds A plus B. Okay, last instruction, move into a pointer C. So we're going out to memory, destination first, out to memory at something called C from EAX. Okay, so C equals whatever's in there. What is in there? That is A plus B. And actually, when you try to read disassembly, sometimes going backwards can be somewhat helpful. As you see this, you go, oh, I'm saving something into C. Saving something into C. What am I saving into C? EAX. What is EAX? You look up, you know, oh, EAX came from here. So it's an add of B. Well, what is it adding? You look up. Oh, it was adding A. So C equals A plus B. All right, next instruction. So we did this instruction. Where's the program going to go after this? So let's say if B add was true, we load that into EAX. We test 1, 1, jump if equal. No, it is not equal. Then again, because that means is it equal to 0? Was it not equal to 0? No, it was not equal to 0. So we do this, we load in A, we add B, we store that as C. And then, boop, here's that unconditional jump. Unconditional jump. So no matter what, you're going to take this jump. It's just a go to, and it says to go to here. Where is that address? 495319. That is 495316. It's just right off the end. So I didn't include that part. That's going to go here. So what is that for? That is to jump over this bracket. When you see this by itself, when you see it just an unconditional jump, a lot of times that's your else statement. It's just jump it out. Okay. So what if BAD had been false? If BAD was false, we load a 0 in here, we test 0 against itself, we get 0, jump if equal to 0 to 310 hex. That's here. What do we do next? We load into EAX from A. We subtract, there's sub, let's subtract from EAX the value we find in B and stick it back in EAX. And then we move out to C from EAX. So that this is, as you see right here, that's C equals A minus B. So that's what the disassembly looks like. All right, just I'll throw these at you really quick. We really won't be using these, but in the 32-bit machines of the olden days, we had these floating point commands. The original machines, those 8-bit machines, did not have floating point registers. When they added floating point registers, they added a whole new set of registers. And so they get new instructions to use those registers. And that's what they look like. So there's they split the move into load and store. That's what that is. The rest of these are pretty obvious. They're just the math functions with an F in the front. Okay. These days, this is the reason you don't need to know these. These days, you're going to mostly see the MMX instructions. And we'll get more into those in the next slides. But what are the basic MMX instructions? Move, here's your move, and I'll have an SS. So what does SS stand for here? Scalar single. What does that mean? What's a scalar single? Scalar means not a vector. Single means single precision float. So an SS is assembly language for float. So get me a float, or move a floating point around from memory into a register, something like that. And all of the math functions have that same pattern. So it's just add SS, mul SS, div SS. You get it. Let's look at an example. So here's that same badd function recompiled where the variables are now floats. These are all floats. And so it looks a little bit different. It's mostly the same, right? So we're still going to have a Boolean for the badd. So this block is exactly the same. And then here, these are floats instead of integers. So we're going to use the SS instructions. And you'll see that the register has a different name. We're not putting this in the EAX register. We're using the XMM0 register. These scalar singles, these vectors, these are actually vector SIMD registers, and we'll talk about them in the further slide. But they started naming them differently. They just call them the XMM for these extended, multi-value registers, and they just count them off from 0, 1, 2, 3. Instead of going ABC, they just said 0, 1, 2, 3. Okay, but as otherwise it's the same. So we load into XMM0 from A, we add into XMM0 from B, we store, there's a move out to memory, we store into C from XMM0. Here's your same jump, and there's the same shenanigans with the subtract. Okay,